Hello, ladies and gentlemen, and welcome to another wonderful lesson with Mr. Wheezy. So, moving on, we're jumping ahead. We're kind of leaving in the middle of Chapter 3. Now, the rest of Chapter 3, not that it's not important, but just wanted to hit these last three lessons so you have a little bit of a taste of what antiderivatives, aka indefinite integration, is, what integrals are. The rest of Chapter 3, what we're really getting into is we already talked about the first derivative test, which tells us whether it's increasing or decreasing. We also get into the second derivative test, which is telling you which way it's curving. So are we curving up to make like a minimum, or are we curving down to make like a maximum? We get into that and really get into how we can get all this information from an equation of what the graph's all going to look like just by doing the different things with derivatives. That's really what was tying up Chapter 3. I'm sorry you're missing out on that. Normally, in a normal year, we would have hit those, but we're going to skip ahead to this. So, I'm also going to skip over the kickoff because that's relating back to derivatives. We're going to move forward to the antiderivative. So think derivative, we're reducing it down. We're breaking down that equation to find stuff. Antiderivative, we're going backwards. We're building it back up. So think derivative, if we find the derivative of something, we get its prime, so like the first derivative, f prime. Well, the integral here, the antiderivative, then goes backwards back to the original. So the function f is antiderivative of f on the interval if f prime of x is f of x for all x and I. So basically, like I said, you're just going backwards. You're finding back to that original equation. So if you found the derivative, this is going back to the original. So, think we did the derivative, we got 3x squared. Well, what was that original equation that got that? Well, we would have took the exponent, bring it down, and subtracted 1. So if we go back, we add 1 to the exponent, and we get rid of, so we're going to divide it by that number. So going backwards, that would have got us x plus 3. Now, there could have been a constant that when we did the derivative of would have disappeared. So we're going to do, when we do this, we'll find the integral, and then we do a plus c. And later on, we're going to find how to find what that c is. But for right now, just know you add a plus c, which is representing, hey, maybe there's a constant here. Maybe it was just 0, maybe it's nothing. But we're still going to do a plus c just in case there is. So when we do the capital letter, that's doing the antiderivative. Later on, I'll tell you it's also called the integral. But just know that that's what that's meaning. So if we find the antiderivative of y prime equals 2. So if we did the derivative and we just got a number, that was when we just had an x. So our original y. So we're y prime, the first derivative, going back to the original y, would have been 2x plus a c, a constant. So we're building this back up. Doing the derivative, we lost that x. Going backwards, we're getting that x back. So a lot of times when you do that, when we did derivatives, we did that dy over dx, or we did f prime sort of a thing. So if we actually solve this out to find what dy is, we would get f of x dx. So that's really the form we need it to be in order to do the derivative. So you'll see the little squiggle like this. That means integral of f of x dx. So whatever the derivative of this function was, that'll give us back to the original function plus whatever that constant is. So we're calling this indefinite integrals because we're doing this for any x in this equation. So any value could work here. We're not narrowing it down. We're going to get into narrowing it down in the next lesson. So that's kind of some foreshadowing. So in your notes here is a big, huge chart of how to do the derivatives. Right now, we're mainly going to focus on these first couple here. So remember, if there was a constant there when we did the derivative, we got 0. So keep in mind, if you're going to do the integral of 0, you're going to get constant back. Okay, if we had a number times x, when we did the derivative, it was just that number. So when we go backwards, if we're doing the integral of a number, we're adding that x plus a c. So it's just like that last example we just did. When we had 2, we added an x plus a c to it. If we have that constant multiple, we do the derivative and then everything's times it while going backwards. Same thing. We can really pull that constant out front, find the integral of it, and then times that integral back in. Power rule. This was one we did. So we took that exponent, moved it to the front, and then subtracted 1 from that power. Well, here we're going backwards. So if we're x to the nth, we're going to add 1 to that exponent and then divide by that new exponent. So we're going backwards. And that's what I'm going to show you here in a little bit. The rest of these are trig functions, which we'll get into a little bit. Now, with these, you might have to do some manipulation. And again, we'll cover an example like that. So hang in there. But if we want to do the antiderivative, so the integral of 3x. So if we go backwards, 3x, well, there's no exponent in front, or there's no exponent here, so when we add 1, this is technically to the first, so this becomes squared. And we're going to divide by whatever that new exponent is, squared. And so we add a plus c, and that is our original function. So if you think about it, if we did derivative of this, derivative of c would go away and be gone. We would bring the 2 down in front, which would cancel with the 2, and we'd be left with 3x, because then we'd minus the 1, make that to the first, and we'd put it back there. So we're just going backwards. So if we do these different ones here. So right now there's nothing here. So think of there's technically a 0 in there. When there was a 0, that went to just the constant. Actually, I take that back. There should be a 1 here. So that would be an x plus the constant. That was my bad. Sorry. Nothing there. So yeah. Should be a 1, not a 0. If it was a 0, there wouldn't be anything there. So going backwards from x. Well, technically this is x to the first, so we would get x squared and then divide by that new exponent. The 2 didn't have anything, so it would just get an x, and then we always have to do the plus c. If we do this one here, so 3x to the 4th, we would add 1 to make this to the 5th, but then we divide by that new exponent over 5. Minus 5x squared becomes to the 3rd over 3, plus x will become squared over 2 plus your constant. So power rule in reverse. That's how the integral goes. It builds it back up. Because again, if we would have done the derivative here, we would have brought that 5 down, which would have canceled with the 5, which left us with 3x to the 4th after we subtract 1. Same thing here. Bring the 3 down, cancels with the 3, so 5x squared is our next one. Here, bring the 2 down, they cancel, so you just have an x. So yeah, just going backwards, so doing the opposite thing. Now, sometimes you may need to do some manipulation. Right now, looking at this, we would have to do like the quotient rule of integrals. We're not going to do that. We're going to keep this simple. We're going to start by, and that's a bad integral symbol. So separating this out. So we would have x over, and the square root of x, I'm going to write as x to the 1/2, plus 1 over x to the 1/2. So if you think about it, that's to the first, and then don't forget your dx on the backside. And then that's just saying that, hey, this is the derivative, so then what would that integral be? When we have the same base and they're divided, we can subtract them. So integral of x to the first over x to the 1/2, 1 minus the 1/2 would make this x to the 1/2. Plus, here, it's just on the bottom, so if we bring it to the top, it makes it to the negative 1/2 dx. Now we can just do that power rule again. So, x to the 1/2, we would add 1 in to make this x to the 3/2. We would then divide by 3/2. And we'll do a leaf change flip in a moment. Here we'd add 1 to make this x to the 1/2. Again, we divide by 1/2. So when it flips, we would have 2/3 x to 3/2 plus 2, well, it's just going to be 2 x to the 1/2. And we're going to leave it like that. Because from there, oh, and don't forget, we need a plus c as well. So 2/3 x to 3/2 plus 2x to 1/2 plus c will be your final answer. Now we could put the roots back in. We're just going to leave it like this for right now. As far as trig functions go, again, here, this doesn't necessarily match up with anything. So we got to do some manipulation. So what I'm going to do is I'm going to split this up here into a couple of different factors. So the integral of sine x over cosine x times 1 over cosine x. Because sine times 1 would be sine, or cosine, cosine squared. So what that allows me to do is sine over cosine. If you think back to the trig function or trig identities, that's going to be tangent x. 1 over cosine is the same thing as secant x dx. So if we would look back at our little chart here, so cosine, sine, secant squared, we have a secant tangent. Close, we just have a different order. Remember, multiplication is commutative. We can rewrite this as secant x tangent x dx. Because it's commutative, then that fits that one, which means this is going to go to secant x plus c as the antiderivative. So, may have to do some manipulation like that. Now, the last little bit I want to hit is, well, sometimes we can find that particular solution for what our c is. So it might give you, okay, f of 2 equals 4, so then we can put that back in and find what we're missing there. So here we're going to deal with our derivative is 1 over x squared, where x is greater than 0. So then find the particular solution that satisfies the initial condition of f of 1 equals 0. So, start by setting up our integral. So 1 over x squared dx. So because we know that was the derivative, we're putting the dx in there. Well, that's what we need to go backwards. So we're saying, hey, this was a derivative. We got to build this back. Because if it wasn't a derivative, or if it's not able to be a derivative, I should say, then that makes it really hard to find the integral if you couldn't have done the derivative of it, kind of a thing. So, I'm going to rewrite this though. This, if we move to the top, is really x to the negative half, or negative 2, sorry. So when we do the power rule, we would have x, and if we add 1 to that, to the negative first, we would divide them by negative 1 plus c. So in other words, we have negative 1 over x plus c as our integral. So now it says, hey, f of 1 is going to be 0. So if we do f of 1, negative 1 over 1 plus c would have to equal 0, is what that's saying. So now the only thing we don't know is c, so we can solve from there. So keep in mind this is really minus 1, negative 1 over 1. So if I add 1 to the other side, c equals 1. So our real equation, I guess I should say then, is negative 1 over x plus 1. And that would be your final. So that's kind of how you go back through and solve. So you'll do the integral, and then whatever they give you here, you can put that in for x, set it equal to what it's equal to, and then you'll solve out for c. Now, just like how we did Like, say, if y is whatever, we could find the y prime, we could find the y double prime, y triple prime. Well, we can do the same thing going backwards, and it'll give you what that is. So it might say, okay, well, f prime of x, or of 1 is 2, and then f of x is 3 or whatever. And so then once you find the first derivative, then you can go through and find, okay, what's my c? Do the second derivative, or integral. Sorry, once you do the first integral, put that in. Second integral, put that in, and yada yada. So, that is it for this lesson. Let me know if you have any questions, comments, or concerns. Again, please reach out to me on Google Classroom, or email is what I get back to you the quickest. Otherwise, do pan me too, but just know I don't check that as often. So, have a good day, and we will talk to you guys later.